On the morning of May 18th, 1980, the sky over Portland, Oregon began to go wrong in a way no one could explain. There were no storm clouds, no smoke on the horizon, no distant thunder, just fine gray ash drifting silently down onto cars, rooftops, and sidewalks, as if the air itself were dissolving. People stepped outside, looked up, and found nothing. The mountain responsible stood 50 miles, about 80 kilometers away, and it had already made its move. Portland never heard a sound. That silence was not an accident. What erupted that morning produced a shock wave powerful enough to be heard in British Columbia, in Montana, in Northern California, yet the nearest city heard absolutely nothing. Scientists would later call it the quiet zone, a strange trick of atmospheric physics that swallowed the sound whole and carried it elsewhere. 50 miles, 80 kilometers away, the mountain had just changed shape. In a matter of seconds, the entire northern face of Mount Saint Helens collapsed in the largest landslide in recorded human history. The pressure holding the volcano together vanished in an instant, and what followed was not a normal eruption. The mountain did not blow upward, it blew sideways. A superheated wall of gas, rock, and ash exploded northward at close to the speed of sound, flattening forests across an area larger than the city of Chicago, reaching temperatures hot enough to incinerate everything in its path. A volcanologist at an observation post 6 miles, roughly 10 kilometers away, a post that was supposed to be in the safe zone, had just enough time to radio 6 words before the blast reached him. Vancouver! Vancouver! This is it! His body was never found. The ridge where he stood is named after him today. A photographer 4 miles, about 6 kilometers from the summit, watched the wave of ash coming and understood what it meant. He kept shooting until the last possible moment. Then he rewound his film, placed it in his backpack, and lay himself down on top of it. When rescuers found him 17 days later, the photographs were intact. They were published in National Geographic. They are still some of the most haunting images ever taken. What happened on that mountain overturned nearly everything volcanologists thought they understood about how volcanoes work, about what they could do, how fast they could move, and how little warning they might give. This is the story of the morning America's deadliest volcano erupted in the wrong direction and what it left behind. If this is the kind of content that keeps you up at night in the best possible way, take a moment to like this video and subscribe. It genuinely helps bring more stories like this one to more people. And let me know in the comments, where are you winding down tonight? And what's the time over there? It's always a joy to see people from different parts of the world listening to these stories. Now, let's go back to Mount St. Helens before it all started. Before the mountain became a name spoken alongside disaster, it belonged to postcards, family albums, and long summer afternoons. Mount St. Helens rose above southwestern Washington with a near perfect volcanic cone capped in snow, reaching 2,950 meters, which is about 9,679 feet. From valleys and highways, its balanced profile appeared so graceful that generations of visitors affectionately called it the Mount Fuji of America, a comparison inspired by its elegant symmetry and striking outline against the sky. Its slopes had rested since 1857. Across 123 years, forest matured into towering communities of Douglas fir, western hemlock, and cedar. Moss covered fallen trunks, streams threaded through the woods, and wildlife moved through habitats that had known little interruption for more than a century. At the northern foot of the mountain, Spirit Lake reflected the changing seasons, drawing campers, anglers, boaters, and families who returned year after year. Logging roads crossed the surrounding national forest, supporting an industry that had become part of everyday life across the region. Beyond this single peak stretched the Cascade Range, a chain of volcanoes extending from British Columbia to Northern California. More than a dozen major volcanic mountains stood across that landscape, each shaped by the slow descent of an oceanic tectonic plate beneath the continent. Since the eruption of Lassen Peak in 1915, none had produced a major volcanic event. Two generations had grown up with these summits filling the horizon, admired as landmarks instead of active geological systems. The appearance of permanence concealed a different story written across thousands of years. Mount Saint Helens was the youngest major volcano in the Cascade Range, and also its most frequently active during the recent geological past. Over roughly 4,500 years, repeated eruptions had built and reshaped its cone again and again. Geologists from the United States Geological Survey examined that history carefully and concluded that this mountain carried the greatest likelihood of erupting within the coming decades. Their report circulated among scientific circles, yet very few people beyond that community ever encountered its conclusions. Near the lakeshore stood Spirit Lake Lodge, where Harry Truman had welcomed visitors since 1928. Spread across 50 acres, which is about 20 hectares, the property became a familiar destination for fishing trips, cabins, boats, and evenings spent overlooking the water. For 52 years, he watched children return as adults and then bring families of their own. The lodge carried memories accumulated through ordinary seasons, making it far more than a business. It had become the landscape of his entire adult life, woven together with friendships, routines, and the mountain itself. Morning arrived on March 19th, 1980, with little to separate it from countless other spring days. Snow still crowned the summit, boats rested along the lakeshore, timber crews prepared for another day of work, and visitors admired a mountain whose graceful outline appeared unchanged. Across the forests and valleys, life continued with familiar rhythm, while deep below that beautiful cone, forces already gathering prepared to announce themselves through the first movement of the ground. The first sign arrived from deep within the mountain, where rock shifted beyond human sight before any change appeared on the surface. On March 20th, 1980, an earthquake measuring 4.2 in magnitude rippled through the ground beneath Mount Saint Helens. It was the strongest seismic event recorded there in well over a century. During the days that followed, one tremor blended into the next until hundreds of earthquakes formed an almost continuous sequence, suggesting that molten rock was forcing its way upward through fractures hidden inside the volcano. A week later, on March 27th, the summit opened for the first time since the 19th century. The eruption carried ash and steam about 2,100 meters into the sky, which is about 6,890 feet. Fresh magma never reached the surface during this event. Rising heat encountered groundwater trapped inside the mountain, transforming liquid into expanding steam with tremendous force. The explosion carved a new crater through snow and ice, scattering ash across the surrounding landscape, while reminding geologists that activity had entered a new phase. News spread rapidly across the United States. Television crews, newspaper photographers, and reporters traveled toward the mountain, alongside curious visitors hoping to witness history. Scientists from the United States Geological Survey established observation stations, installed instruments, and collected samples whenever conditions allowed. The United States Forest Service restricted access to hazardous areas, although pressure from residents, businesses, and property owners complicated those decisions. Each passing week attracted wider attention, turning the volcano into a subject followed daily by millions. Measurements soon revealed a transformation unlike anything previously documented in such detail. Laser instruments, aimed across the northern slope, detected steady outward movement instead of collapse. The mountainside expanded farther each day, eventually advancing almost 2 meters every 24 hours, which is about 6.6 feet. This remarkable swelling reflected magma pushing sideways into the volcano's northern flank, stretching solid rock outward like a slowly inflating shell. By May 17th, the bulging face had shifted roughly 140 meters from its earlier position, which is about 459 feet. The distortion had become visible without scientific equipment from many observation points surrounding the volcano. Geologists recognized that the expanding rock could not continue indefinitely. Every fresh survey showed increasing strain, as though the mountain were carrying a growing weight that could no longer remain supported by its own structure. Among those watching most carefully was David Johnston, a volcanologist who had spent weeks collecting volcanic gas samples and helping establish monitoring stations. He repeatedly argued that exclusion zones should extend farther from the summit because the deformation suggested a danger greater than existing hazard maps allowed. Describing the volcano as a dynamite keg with the fuse already burning, he expressed concern rooted in careful observation instead of dramatic language. His colleagues respected both his caution and his deep familiarity with the changing mountain. During the evening of May 17th, Johnston agreed to replace a colleague assigned to the Coldwater Observation Post after an unexpected scheduling conflict. He carried his equipment onto the ridge, organized his instruments, and prepared for another routine night of measurements. A photograph taken before sunset showed him seated beside his notebook, relaxed beneath clear spring skies. Early on May 18th, routine observations revealed nothing unusual. Around 150 kilometers away, which is about 93 miles, people in Portland welcomed another pleasant Sunday morning, unaware that the mountain had entered its final hours before release. Time narrowed to a single instant on the morning of May 18th, 1980. At exactly 8:32 and 11 seconds in the morning, Pacific Daylight Time, an earthquake measuring 5.1 in magnitude broke beneath the northern slope of Mount Saint Helens. For weeks, the volcano had stretched against its own weight. Now, the force holding that strained mountainside together reached its limit. Within only a few seconds, the entire northern face began to separate from the volcano. Roughly 2.5 cubic kilometers of rock, glacier, ice, snow, and the pressurized dome of magma hidden inside the mountain, detached as one enormous mass. It accelerated downslope at nearly 250 kilometers per hour, which is about 155 miles per hour. Every moment removed another layer of rock that had confined tremendous internal pressure. The landscape itself became part of the eruption before any towering ash column had formed. David Johnston watched those first moments unfold from the Coldwater. Two observation posts, positioned 10 kilometers from the summit, which is about 6.2 miles. His station faced directly toward the unstable slope. No scientist had ever witnessed an event of this kind from such proximity. As the mountainside collapsed, Johnston reached immediately for his radio and transmitted the words that would become permanently linked with his name. Vancouver, Vancouver, this is it. The message was directed toward the United States Geological Survey Office in Vancouver, Washington. Those listening heard only fragments. The eruption itself may have disrupted the signal before it could be received clearly. Fortune preserved the transmission through an unexpected source. A nearby amateur radio operator had connected a recording device to his equipment, capturing Johnston's final broadcast. After those 5 words, Several distorted sounds followed. Their meaning has never been understood with certainty. The recording then ended. Johnston was 30 years old. His observation post, including its trailer, scientific instruments, communication equipment, and the folding chair seen in the photograph taken the previous evening, disappeared beneath the eruption. More than a decade later, state highway workers uncovered scattered remains of the trailer buried within volcanic deposits. Johnston himself was never recovered, despite extensive searches across the devastated terrain. His death carried a painful contradiction. Among the scientists studying Mount Saint Helens, Johnston had argued most consistently that the restricted zone surrounding the volcano should extend farther outward. He believed the growing deformation along the northern slope represented a danger beyond existing hazard maps. The position assigned to Coldwater 2 had been considered outside the expected range of destructive volcanic activity, according to accepted models of that time. Those models anticipated eruptions rising primarily upward. They had never accounted for the possibility that an entire mountainside could fail and release its energy sideways with overwhelming speed. Years later, the ridge where Johnston spent his final hours became home to the Johnston Ridge Observatory. Completed in 1997, it occupies nearly the same vantage point, overlooking the broad horseshoe-shaped crater left behind by the collapse. Visitors now stand where instruments once watched the changing volcano, looking across the same distance toward the summit, tracing with their own eyes the direction from which one scientist witnessed a geological event that permanently reshaped the understanding of volcanic eruptions. Some lives become inseparable from a place until the two seem impossible to imagine apart. Harry Randall Truman belonged to Spirit Lake in that way. Born in West Virginia in 1896, he served during the First World War before moving west in search of a different future. In 1926, he leased property from the Northern Pacific Railway along the lakeshore and began building what would become the Mount Saint Helens Lodge. The mountain watched over every season that followed, becoming part of the rhythm of his everyday life. The lodge welcomed visitors through the Great Depression, through the Second World War, and through decades of peaceful summers that followed. Families returned to fish, launch boats, rent cabins, and spend evenings beside the water. Harry managed the property alongside his wife, Edna, whom he affectionately called Edie. Speaking years later, he remembered her with uncomplicated warmth, saying she was a beautiful woman whom everyone loved and knew as Eddie. Their partnership shaped the lodge for more than 3 decades, making it a destination remembered across the Pacific Northwest. Everything changed in September of 1975 when Edna died from a heart attack. Friends noticed that Harry never truly recovered. Cabins fell into disrepair. Repairs became less frequent. Reservations declined. Whiskey occupied more of his evenings than guests did, remaining at Spirit Lake no longer centered on business. Every path, every window, and every familiar view carried reminders of the years he had shared with Edna. Leaving would have meant abandoning the place where those memories still seemed closest. As volcanic unrest increased during March and April of 1980, evacuation orders gradually expanded around Mount Saint Helens. Harry refused every request to leave. Newspapers and television crews quickly discovered an elderly innkeeper whose blunt language and unwavering confidence fit neatly into headlines. He declared that the mountain would never harm him and repeated that if it went, he would go with it. Across the country, many people admired the image of stubborn independence presented in those interviews. Far fewer reports lingered on another statement he made. Harry explained that if he lost his home, he believed he would die within a week because he could not bear living anywhere else. Those words carried the weight of grief more than defiance. Spirit Lake had become the last place where life with Edna still felt complete. Staying there reflected an attachment built over decades instead of a desire to challenge the mountain itself. On May 17th, local law enforcement visited once more, hoping persuasion might succeed where earlier efforts had failed. Harry remained unconvinced. He even remarked to nearby residents that the volcano appeared to be settling down. Less than a day later, at 8:32 in the morning, the enormous debris avalanche swept across Spirit Lake. The site of the lodge disappeared beneath approximately 46 meters of volcanic debris. That is nearly 151 feet. Harry and his 16 cats were there when it arrived. Scientists believe the intense heat claimed his life almost instantly, leaving no opportunity for awareness of the event itself. Recovery teams never searched for his remains. Spirit Lake still occupies that valley today, although its surface stands about 60 meters higher than before, which is about 197 feet, supported by the immense volume of debris forming its southern margin. Deep below the altered shoreline rest the remains of the Mount Saint Helens Lodge, Harry's pink Cadillac, photographs that once decorated the walls, and Harry Truman himself, exactly where he always believed he would remain. Some people spend years waiting for a single photograph. Robert Landsburg spent much of the spring of 1980 returning to Mount Saint Helens, believing the mountain was approaching a defining moment. A professional photographer from Portland, 48 years old, he had visited repeatedly as volcanic activity increased. Days before the eruption, he wrote in his journal that he felt right on the verge of something. The words carried expectation, though neither he nor anyone else could have imagined how completely that expectation would be fulfilled. On the morning of May 18th, Landsburg drove his station wagon toward the South Fork of the Toutle River, stopping less than 6 kilometers from the summit, which is about 3.7 miles. His camera was already prepared when the earthquake struck at 8:32 in the morning. As the northern side of the volcano began to collapse, he started photographing almost immediately. Every exposure preserved another fraction of a rapidly changing landscape that no camera had ever recorded before. The earliest photographs captured the immense landslide as it descended from the mountain. Frame after frame revealed the expanding cloud that followed, growing broader and denser with astonishing speed. The final image showed little except a wall of dark ash stretching across the entire view, advancing over the terrain with overwhelming force. Looking through the camera, Landsburg recognized what those changing shapes meant. Escape had already become impossible. His remaining seconds unfolded with remarkable clarity of purpose. Landsburg rewound the exposed film into its protective canister, removed it from the camera, and placed both inside his backpack. He set the backpack on the seat of his vehicle, then lowered himself across it, using his own body as the final layer of protection. The sequence required calm decisions completed under extraordinary pressure. He could no longer preserve his own life, yet he could still preserve the record of what he had witnessed. The lateral blast passed first. Fine volcanic ash followed in enormous quantities, filling the air with particles capable of entering every breath. Investigators later determined that Landsburg died from asphyxiation caused by inhaling that ash. Temperatures at his location reached approximately 425 degrees Celsius, or 797 degrees Fahrenheit. Even under those conditions, the backpack shielded the film well enough for its contents to survive. 17 days later, on June 4th, search teams located the station wagon beneath layers of volcanic deposits. Landsburg's body still rested above the backpack, exactly as he had positioned himself. Inside, the film canister remained intact. When technicians developed the photographs, they recovered a sequence unlike any other in the historical record. The advancing blast appeared exactly as Landsberg had seen it from ground level. Heat had also marked the film itself, producing light leaks and physical damage across the emulsion, leaving traces created by the eruption upon the images documenting it. In January of 1981, National Geographic published those photographs. It marked the first appearance of Landsberg's work in the magazine he had long hoped to reach during his career. Decades later, while filmmakers prepared a documentary during the middle years of the 2020 decade, his original camera remained with his family. His journals could still be read, and that final roll of film continued to offer the closest human view ever preserved of the moment. Mount Saint Helens transformed forever. The immense landslide marked the beginning of the catastrophe, although it was only one movement within a much larger chain of events. Its greatest consequence came from what it uncovered. For weeks, the northern side of Mount St. Helens had been swelling as molten material pressed steadily into the volcano. That growing mass remained imprisoned beneath layers of solid rock until the mountainside collapsed and removed the barrier holding everything in place. Geologists call this hidden body of magma a cryptodome. Unlike a magma chamber resting deep underground, a cryptodome forms when hot, gas-rich, partly molten rock forces its way into the flank of a volcano without breaking through the surface. During the months before the eruption, the cryptodome expanded sideways into the northern slope, stretching the mountain outward while enormous pressure accumulated inside. The surrounding rock acted like a massive stone lid, preventing those gases from escaping. When the landslide swept away that confining weight, the cryptodome decompressed almost instantly. A familiar comparison comes from a bottle of carbonated water that has been shaken vigorously before its cap is removed. Dissolved gas escapes with explosive force once pressure disappears. Inside Mount St. Helens, the same physical principle unfolded on a scale measured in cubic kilometers and at temperatures exceeding 300 degrees Celsius, or 572 degrees Fahrenheit. Expanding volcanic gases shattered the molten rock into countless fragments, releasing energy almost beyond comprehension. The eruption that followed did not travel upward through the summit in the way scientists had long expected from explosive volcanoes. It burst through the newly opened northern side of the mountain, producing an immense lateral blast that raced across the landscape. Initial velocities approached 350 kilometers per hour, which is about 218 miles per hour. Along its leading edge, the expanding cloud accelerated to nearly 1,080 kilometers per hour, which is about 671 miles per hour, approaching the speed of sound under those atmospheric conditions. Its path left distinct zones of destruction that remained visible long after the ash settled. Within the innermost 10 kilometers, which is about 6.2 miles, nearly every trace of the former landscape disappeared. Soil vanished, exposed bedrock emerged, and forests gave way to open deposits of volcanic debris. David Johnston's observation post stood within this region, overwhelmed almost immediately after the blast began. Farther outward stretched the immense blowdown zone, extending from roughly 10 kilometers to 30 kilometers, which is about 6.2 miles to 18.6 miles. Towering Douglas fir trees reaching about 60 meters in height, that is nearly 197 feet, snapped like brittle stems or were lifted entirely from the ground. Around 10 million trees fell into remarkably consistent patterns, all pointing away from the volcano across approximately 600 square kilometers, which is about 232 square miles. Beyond that lay a broad belt where many trees remained upright, yet intense heat had ended every living tissue within them. Core temperatures exceeded 350 degrees Celsius, or 662 degrees Fahrenheit, while even the outer margins remained hot enough to destroy life without toppling the trunks themselves. Across nearly 230 square miles of terrain, an area comparable to the city of Chicago, the landscape transformed within minutes. Timber losses alone were estimated at roughly $500 million, leaving behind a record that permanently reshaped the scientific understanding of volcanic eruptions. While the lateral blast swept across forests and valleys, another transformation unfolded above the broken mountain. The collapse of the summit stripped away the rock that had covered the volcanic conduit, leaving a direct passage from the rising magma to the open atmosphere. Through that opening, an immense vertical eruption column surged skyward from the newly formed horseshoe-shaped crater, carrying ash, volcanic gases, and shattered fragments of rock high above the surrounding landscape. Its ascent was astonishingly rapid. Within only 10 minutes, the column climbed to about 24 kilometers, which is about 15 miles, reaching well beyond ordinary weather systems and extending into the stratosphere. Rising gases continued feeding the plume without interruption for approximately 9 hours. Every passing minute carried another immense pulse of material into the upper atmosphere, where prevailing winds gradually took control of its direction. Those winds pushed the ash cloud toward the northeast, sending it across eastern Washington before it continued over Idaho and Montana. Communities far removed from the volcano watched daylight disappear beneath an advancing gray ceiling. Spokane, located about 400 kilometers away, which is about 249 miles, experienced one of the most striking transformations. Near midday, darkness spread across streets that only moments before had rested beneath a clear spring sky. Automatic streetlights flickered on. Drivers eased their vehicles onto the roadside because familiar landmarks disappeared behind the dense airborne ash. The material falling from above looked soft at first glance, yet each grain carried remarkable destructive power. Volcanic ash differs from the soot produced by fire. It consists largely of microscopic fragments of volcanic glass formed when erupting lava cools so rapidly that it shatters instead of crystallizing. Every tiny particle possesses sharp edges capable of grinding away moving machinery. Automobile engines, aircraft turbines, electronic equipment, and ventilation systems all suffered damage when ash entered their working parts. Breathing also became hazardous as those fine particles settled deep within the lungs. The cloud continued traveling long after the eruption itself weakened. Measurable ash deposits eventually appeared across 11 states within the United States and several Canadian provinces. Detectable traces reached locations as distant as Minnesota and Oklahoma. Atmospheric monitoring stations later confirmed that suspended volcanic particles completed a journey around much of the northern hemisphere, demonstrating how a single eruption could influence skies thousands of kilometers from its source. Scientists estimate that approximately 4.2 cubic kilometers of material, which is about 1 cubic mile, erupted from Mount Saint Helens during the event. Roughly 1 cubic kilometer, which is about 0.24 cubic miles, consisted of fresh magma rising directly from within the volcano. The remaining volume included older rock torn apart during the eruption. Spread evenly across an area measuring 1 square kilometer which is about 0.39 square miles. That material would have formed a layer nearly 4 kilometers deep, which is about 2.5 miles. Communities across eastern Washington spent many weeks clearing ash from rooftops, roads, gutters, and drainage channels before ordinary routines returned. Yakima alone devoted approximately 10 weeks and more than $2,200,000 to cleanup efforts. More than 1,000 commercial flights were canceled as airports across the Pacific Northwest suspended operations. Those who experienced the day often remembered the same details afterward: gray skies replacing blue, gritty dust covering every surface, familiar outdoor sounds fading beneath the muffled air, and the sharp scent of sulfur lingering where spring usually announced itself through rain, soil, and evergreen forests. Far below the towering eruption column, the river valleys were undergoing their own transformation. The violence unfolding there attracted far less attention in the first moments, yet it would reshape waterways across an enormous region. These flows raced through channels that had guided rivers for thousands of years, carrying entire landscapes downstream with astonishing force. For communities beyond the volcano itself, this became one of the longest lasting consequences of the eruption. The upper slopes of Mount Saint Helens had long been covered by glaciers and deep seasonal snow. When the eruption released tremendous heat, much of that accumulated ice vanished within moments through rapid melting and vaporization. Water immediately mixed with volcanic ash, shattered rock, uprooted forests, and loose sediment. Gravity gathered this mixture into immense torrents called lahars. Unlike ordinary floods, lahars become denser as they travel, collecting additional debris until they resemble flowing earth more than flowing water. A lahar is best understood as a volcanic mudflow with the consistency and density of wet concrete. It does not behave like thin, muddy water. Every surge carries extraordinary weight, allowing it to transport objects that would appear impossible to move. Massive boulders, the size of automobiles, rolled within the current. Douglas fir trees, reaching 60 meters tall, which is about 197 feet, drifted through the flow as though they had little mass. Entire hillsides dissolved into the advancing mixture, adding fresh material with every passing kilometer. The largest lahar followed the North Fork Toutle River toward the northwest. During the first 10 minutes, it traveled approximately 21 kilometers, which is about 13 miles. At its leading edge, the flow reached speeds close to 145 kilometers per hour, which is about 90 miles per hour. Bridges disappeared almost instantly after the torrent reached them. Riverbanks vanished beneath thick volcanic deposits. Across much of the valley, fresh sediment accumulated to an average depth of 46 meters, which is about 151 feet, replacing familiar channels with an entirely different landscape. Even after the initial surge passed, additional waves continued moving downstream for many hours. Its influence eventually reached the Columbia River, located about 80 kilometers away, which is about 50 miles. There, millions of cubic meters of volcanic sediment settled into the shipping channel. Before the eruption, vessels relied upon a navigable depth of approximately 12 meters, which is about 39 feet. After the lahars arrived, portions of that channel measured less than 4 meters deep, which is about 13 feet. Ocean-going ships found themselves unable to continue toward Portland. Restoring navigation required months of dredging as engineers gradually removed the enormous volume of newly deposited sediment. Many downstream communities never received specific warnings about lahars before they arrived. Existing hazard planning concentrated primarily on areas close to the volcano itself. Few anticipated that these dense flows could travel such great distances with such remarkable speed. Once they entered inhabited valleys, the available time between first detection and arrival had already disappeared, leaving little opportunity for organized evacuation. The story did not conclude when the currents finally slowed. Sediment carried by the lahars entered an ongoing journey through the watershed. Decades later, the Toutle River continues transporting material released during the eruption, altering channel shapes, gravel bars, and river depths with every season. More than 45 years after that spring morning, the landscape still bears evidence of a flow that began in minutes, yet continues moving through the valleys, one grain at a time. 57 lives ended during the eruption of Mount Saint Helens, yet those lives cannot be gathered into a single story. They belong to people of different ages, occupations, and hopes, each arriving for reasons that made complete sense before the mountain changed. Some came to study a volcano that had occupied their thoughts for weeks. Others came with cameras, convinced they might witness an extraordinary moment. Some were working ordinary shifts in nearby forests. Others sought a peaceful Sunday, surrounded by familiar landscapes beneath a clear spring sky. Among them was David Johnston, a volcanologist with the United States Geological Survey, only 30 years old. Since March, he had devoted himself to measuring volcanic gases, helping establish monitoring stations, and urging officials to consider wider evacuation boundaries. On the morning of the eruption, he occupied the Coldwater 2 observation post after agreeing to replace a colleague. His final radio transmission became one of the best-known moments in the history of volcanology. Johnston himself was never found, his observation post erased beneath the eruption that he had spent weeks trying to understand. Harry Randall Truman remained at Spirit Lake for entirely different reasons. At 83 years of age, he refused repeated requests to leave the lodge where he had lived for more than half a century. The place held the memory of his wife Edna, whose death had reshaped his world years earlier. He often spoke with reporters through humor and stubborn confidence, yet his deeper explanation rarely received equal attention. Leaving meant abandoning the only home where he still felt close to her. Neither he nor the lodge was ever recovered after the debris buried the shoreline. Robert Landsburg, 48 years old, arrived carrying cameras instead of scientific instruments. When the eruption began, he continued photographing until escape became impossible. He protected his exposed film with his own body before volcanic ash ended his life. Search crews recovered him 17 days later, and the preserved photographs became an irreplaceable visual record of the eruption from ground level. Another photographer, Reed Blackburn of the Columbian newspaper in Longview, worked alongside scientific teams while helping document the volcano. Positioned about 13 kilometers from the summit, which is about 8 miles, he had remote cameras prepared for both the United States Geological Survey and National Geographic. His vehicle was located 4 days after the eruption. The film inside could not be saved. The Carr family had chosen the day for reasons far removed from scientific observation. Day Carr had recently sold a photograph of Mount Saint Helens and hoped to capture more images with his wife and children nearby. Their pickup truck encountered the eruption with almost no opportunity to escape. Within roughly 1 minute, the advancing blast overtook them. Other victims included timber workers employed by Weyerhaeuser, who entered restricted areas using authorized work permits. Several operated in locations that scientists had argued should belong within a larger exclusion zone. Their presence reflected the difficult balance between scientific caution, economic activity, and public policy during the weeks before the eruption. The youngest victim was an 11-year-old child. Every name now appears on the memorial overlooking the transformed landscape at Johnston Ridge. In total, 57 people lost their lives. Rescue crews also brought between 125 and 150 survivors out of the devastated region during the following days. Some endured because ridges redirected the blast. Others found unexpected protection inside vehicles or happened to stand beyond the most destructive path. The number remembered today reflects more than tragedy alone. Restrictions around the volcano, though imperfect, prevented thousands of visitors from gathering near the mountain on that bright Sunday morning, turning what might have become one of the deadliest volcanic disasters in modern history into a loss measured in dozens rather than many thousands. History often remembers an eruption through the force that shattered a mountain. Yet another story unfolded in offices, field camps, and observation posts where measurements slowly accumulated into understanding. During the months before Mount Saint Helens erupted, scientists from the United States Geological Survey recognized that this volcano stood apart from the other peaks of the Cascade Range. Earthquakes, ground deformation, volcanic gases, and repeated steam explosions formed a pattern that pointed toward an eruption. Monitoring stations spread across the mountain. Evacuation boundaries were established despite fierce political and economic resistance. And access restrictions remained in place even as frustration grew among residents and businesses. Those decisions almost certainly preserved many lives that otherwise would have been lost. The greatest scientific mistake did not concern whether an eruption would occur. It concerned the direction in which the mountain would release its energy. Operational hazard maps available during 1980 were built around eruptions that rose primarily into the sky. Pyroclastic flow zones, lahar pathways, observation sites, and recommended safe distances all reflected that expectation. The possibility that the mountain could explode sideways existed within scientific discussion, yet it remained outside the practical framework guiding emergency planning. David Johnston had examined deposits from earlier episodes in the volcano's history and concluded that laterally directed explosions had occurred before. He warned colleagues that the swollen northern slope deserved particular attention because its deformation suggested a different style of failure. His interpretation proved remarkably accurate. Even so, transforming an emerging scientific idea into official hazard boundaries required evidence, agreement, and time. The eruption arrived before that process could reach completion. Between knowledge and action lay a narrow interval that carried enormous consequences. Scientists possessed observations that hinted at a broader danger, while emergency planners relied upon operational models designed from the best available understanding of previous eruptions. Those two forms of knowledge had not yet fully merged. 57 people occupied that uncertain space when the mountain failed, revealing that scientific progress often advances through painful correction instead of immediate certainty. The lessons from Mount Saint Helens reshaped volcanology across the world. Laterally directed blasts became a standard element of volcanic hazard assessments instead of unusual possibilities. The Cascades Volcano Observatory was created to strengthen research, monitoring, and communication throughout the volcanic chain. Gas monitoring programs, inspired by David Johnston's work, expanded into one of the most valuable methods for recognizing magma rising toward the surface, allowing scientists to compare changing chemical signals with seismic activity and ground deformation before future eruptions. Those advances demonstrated their value only 11 years later. In 1991, Mount Pinatubo in the Philippines displayed growing signs of a major eruption. Several scientists whose experience had been shaped by Mount Saint Helens joined Filipino and American colleagues in evaluating the evidence. Together, they urged authorities to order a broad evacuation before the volcano reached its climax. Tens of thousands of people left vulnerable communities before the eruption began, preserving lives on a scale rarely achieved in volcanic disasters. The success did not erase the losses from 1980. It revealed something equally enduring: that careful observation, honest revision of accepted ideas, and the willingness to learn from failure can transform one mountain's tragedy into protection for people living beside another. A line drawn across a map can appear precise, yet every boundary carries the weight of competing priorities. Around Mount Saint Helens during the spring of 1980, the exclusion zone represented far more than a scientific calculation. It became the meeting place of geology, economics, property rights, public safety, and political judgment. Each adjustment to its boundaries reflected negotiations between those trying to reduce danger and those whose livelihoods depended upon access to the forests surrounding the volcano. Scientists from the United States Geological Survey argued that the unstable mountain demanded a larger restricted area than officials were prepared to establish. Their recommendations grew from earthquake activity, swelling ground, volcanic gases, and other signs that pressure continued to build inside the volcano. They viewed the landscape through measurements and probability. State officials faced a broader set of responsibilities. Every additional kilometer, which is about 0.62 miles, placed behind roadblocks affected businesses, timber operations, tourism, and families with homes or cabins inside the proposed closure. The final boundary emerged as a compromise instead of a purely scientific perimeter. Among the strongest economic voices stood the Weyerhaeuser Timber Company, whose logging rights extended across extensive forests near the mountain. Valuable timber waited within those stands, and each passing week without harvesting carried measurable financial consequences. Company representatives urged continued access for logging crews wherever officials believed work could continue safely. Their requests became part of a larger discussion in which economic losses were measured alongside volcanic hazards, even though those two realities could never be weighed by the same scale. Resistance also came from people who owned cabins, lodges, and recreational property inside the threatened region. Many had spent years building memories there and struggled to accept that government authorities could deny entry to land they legally possessed. Their concerns reached elected representatives, adding another layer of pressure upon officials responsible for deciding where barriers should stand. Governor Dixie Lee Ray balanced the expanding scientific warnings against these political and economic demands, producing an exclusion zone influenced partly by roads, ownership patterns, and practical enforcement, as well as hazard assessments. Special access permits reflected those compromises. On May 17th, the day before the eruption, certain property owners received permission to pass through checkpoints and recover belongings before leaving again. Members of the Smith family, who operated Spirit Lake Lodge, entered the restricted area for that purpose and departed before evening. Harry Truman remained at his own lodge beside Spirit Lake, choosing to stay where memories of his wife still shaped every familiar corner of the property. The consequences of those political decisions became clearer after the eruption. Several logging crews who lost their lives had been working inside areas that would have fallen within the larger exclusion zone proposed by scientists. Their presence did not arise from ignorance of the volcano alone. It also reflected a boundary reduced through negotiation, where acceptable risk had been defined by more than geological evidence. Looking back, The exclusion zone carries two truths that exist together without contradiction. It prevented an even greater catastrophe by keeping countless visitors away from the mountain during a bright spring weekend. At the same time, it remained smaller than many scientists believed conditions justified, leaving people within reach of hazards that later exceeded operational expectations. That tension continues wherever active volcanoes stand near communities today, reminding every generation that public safety is shaped not only by scientific understanding, but also by the difficult choices societies make when knowledge, economics, and human lives converge. The first photographs taken from the air revealed a landscape that no longer matched the maps carried by pilots or the memories held by those who had known the mountain for decades. Mount Saint Helens remained in the same place, yet its identity had changed beyond recognition. The familiar cone had disappeared, valleys had been reshaped, forests erased, and ridges cut open. The eruption had done more than scar the volcano. It had rewritten the geography of an entire region within the span of a single morning. One measurement captured that transformation with startling clarity. Before the eruption, the summit reached 2,950 meters, which is about 1,833 miles. After the collapse and explosion, its highest point stood at 2,549 meters, which is about 1,584 miles. 401 meters of elevation, equal to more than a quarter of a mile, had vanished almost instantly. A volcanic structure, assembled through tens of thousands of years, had lost its upper crown in only a few minutes. Washington's fifth highest peak became its 30th, its former height preserved only in photographs and surveying records. The new crater bore little resemblance to the circular openings, often imagined for volcanoes. Stretching about 3 kilometers, which is about 2 miles, from north to south and 1.5 kilometers, which is about 0.93 miles, across, it formed an enormous horseshoe opening facing north. That shape recorded the sequence of the disaster itself. The landslide had removed the mountain's northern flank, allowing the pressurized interior to burst through the gap. From aircraft, satellites, and the ridge about 8 kilometers away, which is about 5 miles, where David Johnston had worked, the missing side appeared as a broad hollow, replacing the elegant symmetry that had once earned admiration across North America. North of the crater, the terrain displayed a pattern that almost resembled a carefully prepared illustration. Closest to the volcano lay a broad gray core where little remained except shattered rock and fresh volcanic deposits. Beyond that stretched rows of fallen trees aligned in the exact direction of the lateral blast. Farther outward, forests still stood upright, though every trunk had been scorched and every branch stripped of life. From above, the eruption's path could be traced across the landscape with remarkable precision, each zone preserving a different chapter of the same event. The destruction reached far beyond the mountain itself. Economic losses were estimated at about $1,100,000,000 in 1980, equal to roughly $3,500,000,000 today after accounting for inflation. Around 200 homes were destroyed, about 185 miles of roads and 15 miles of railway disappeared beneath debris or were torn apart. Approximately 12 million board feet of commercial timber were lost. Nearly 1,500 elk perished, along with millions of fish and countless birds, insects, and smaller animals across about 600 square kilometers. Scientists later estimated that the eruption released energy equivalent to about 26 megatons of trinitrotoluene explosive, roughly 1,600 times greater than the energy released by the atomic bomb detonated over Hiroshima. Numbers alone, however, could not convey what greeted the first research teams entering the blast zone. They described a landscape emptied of familiar sounds. No birds crossed the sky. No insects filled the air. Streams that had once murmured through forest valleys had vanished beneath fresh deposits. The mountain had finished speaking, leaving an immense stillness where a living landscape had stood only hours before. When the first research teams entered the devastated landscape, they searched for familiar comparisons and found very few. One description appeared again and again in field notes, interviews, and reports. They called it a moonscape. The phrase reflected more than appearance. Across the blast zone stretched an expanse of gray deposits, shattered rock, fallen timber, and exposed earth that seemed stripped of every process normally associated with a living landscape. To experienced scientists, it resembled their imagined vision of a lifeless world more closely than any place they had previously encountered on Earth. Near the crater, fresh pyroclastic flow deposits remained intensely hot long after the eruption had ended. Temperature measurements collected roughly 2 weeks later recorded values approaching 416 degrees Celsius or 781 degrees Fahrenheit. The ground still released heat into the air, and organic material had almost completely disappeared from the closest parts of the deposit. Plants, fallen wood, animal remains, and surface soils had either burned away, decomposed into ash, or become buried beneath thick layers of newly erupted volcanic material. Mineral grains dominated a surface where familiar signs of life could scarcely be found. Farther from the crater, another pattern stretched across the landscape with striking regularity. Forests that had stood for generations now rested on the ground in nearly parallel rows, every trunk pointing away from the mountain. Bark had been stripped away, branches torn free, and root systems lifted from the earth. Even in the damp climate of the Pacific Northwest, researchers recognized that such an immense volume of fallen timber would require many decades to decay naturally. The scale exceeded any practical effort to remove or process it, leaving enormous natural barriers scattered across the valleys. Conditions beneath those fallen trunks appeared equally discouraging. The eruption had buried existing soil beneath volcanic deposits, mixed layers that had formed over centuries, and destroyed much of the living community responsible for maintaining healthy ecosystems. Bacteria, fungi, insects, earthworms, and delicate root networks had vanished across broad areas. Without those organisms cycling nutrients and supporting plant growth, many scientists believe the foundations of the forest itself had disappeared. From those observations, a broad scientific consensus developed with remarkable speed. Recovery, many concluded, would unfold across centuries rather than decades. Early forests might require about 200 years before becoming firmly established, while the towering Douglas fir ecosystem that had occupied these slopes before the eruption represented the product of several centuries of uninterrupted growth. Such communities could not be recreated quickly, regardless of human effort. Land managers responded according to that understanding. The United States Forest Service prepared extensive replanting programs intended to accelerate recovery wherever practical. The Weyerhaeuser Timber Company also began developing plans for reforestation on lands under its management, hoping to restore future commercial forests while stabilizing damaged ground. Those decisions reflected the best ecological knowledge available during the months immediately following the eruption. Yet, the mountain had already begun writing a different story. Beneath the gray deposits, small survivors had endured in places no scientist initially expected. Recovery would begin without planted seedlings, without machinery, and without carefully organized restoration projects. It would emerge from organisms sheltered below the surface when the eruption swept overhead, revealing that life possessed pathways of return far more varied than even experienced researchers had imagined during those first days among the ash. The earliest proof that life had endured did not arrive as a green shoot breaking through the ash. It appeared as a small mammal climbing from the earth itself. A northern pocket gopher emerged from its underground burrow after the eruption, becoming the first confirmed sign that living creatures still occupied the blast zone. While the surface had been reshaped within moments, the world below had followed different rules. Protected by layers of soil, the animal had remained insulated from conditions that proved fatal to almost everything exposed above ground. That protection came from the remarkable properties of soil. Heat spread across the surface with enormous intensity, yet it did not travel deeply enough to reach every underground refuge. The gopher had remained inside its tunnel, while the eruption transformed the mountain overhead. When it finally surfaced, it entered a landscape unlike the one it had known before. Ash covered the ground in every direction. Familiar plants had disappeared, and food was nowhere to be seen. Even so, the animal continued behaving exactly as its species always had, following instincts refined through countless generations. Its next actions seemed ordinary from the perspective of a burrowing rodent. The gopher dug new tunnels through the loose deposits, pushing material upward into small mounds scattered across the gray surface. Those piles contained something the fresh volcanic ash lacked. Mixed into the excavated earth were fragments of the original forest floor, rich with organic matter, microscopic fungi, bacteria, dormant seeds, and countless other living components that had remained sheltered below the eruption. Without any intention beyond making a tunnel, the animal had carried an entire underground community back into daylight. Those scattered mounds soon became the first favorable places for plants to establish themselves. Seeds already present in the older soil encountered moisture, nutrients, and microscopic partners that allowed growth to begin once conditions became suitable. No restoration plan had placed them there. No scientist had planted them. The process unfolded because the ingredients for renewal had survived beneath the ash, waiting until chance and animal activity reunited them with the surface. The same pattern appeared elsewhere beneath the deposits. Ants, beetles, centipedes, and many other small invertebrates also endured underground during the eruption. As weeks turned into months, they emerged in separate locations, creating islands of biological activity scattered across the blast zone. Recovery no longer appeared as a single advancing front. Instead, it resembled countless tiny beginnings, each starting wherever survival had endured below the surface. Plants carried by the wind soon joined those hidden survivors. Fireweed, pearly everlasting, and lupine produced lightweight seeds capable of traveling many kilometers, which is about many miles, on moving air before settling into suitable ground. Lupine proved especially important because its roots hosted microorganisms that captured nitrogen from the atmosphere and gradually enriched nutrient-poor soil. As the plants expanded, they improved conditions for species that would follow, rebuilding the foundation of an ecosystem from the ground upward. These discoveries reshaped ecological thinking. The blast zone had never been completely lifeless. It formed a mosaic where areas of total sterilization existed beside scattered refuges that preserved fragments of the former ecosystem. Recovery spread outward from those surviving pockets instead of advancing only from the distant edges. The mountain revealed that resilience often begins in places too small to notice until life has already started returning. Few places have allowed scientists to witness the rebuilding of an ecosystem from its earliest moments with such extraordinary detail. The eruption transformed the slopes of Mount Saint Helens into a living laboratory that stretched across an entire landscape. Research began almost immediately after the disaster and continued year after year, creating an uninterrupted record that now spans more than 45 years. Every season added another chapter, allowing biologists to observe recovery as it unfolded instead of reconstructing it long afterward from scattered evidence. Before this eruption, ecologists generally described recovery through a model known as relay succession. According to that framework, devastated ground passed through orderly stages. Bare terrain welcomed pioneer species. Those pioneers prepared conditions for shrubs. Shrubs gradually yielded to young forests, and mature forests eventually followed. Each step was expected to prepare the next in a predictable sequence. The concept appeared elegant because it suggested that ecosystems followed a dependable path after disturbance, progressing through recognizable stages toward a familiar destination. Mount St. Helens refused to follow that script. Recovery unfolded unevenly across the landscape, shaped by countless local events that no model could predict. One valley might remain barren, while another supported thriving vegetation. A single seed landing beside a lingering snowbank could establish a flourishing patch of plants. An elk crossing an ash-covered meadow might carry seeds into places no wind had reached. A burrowing animal could uncover buried soil rich with dormant life, while another nearby location remained unchanged. The rebuilding process resembled an unfolding conversation between chance, survival, weather, and geography instead of a carefully ordered procession. As researchers compared these patterns, a new understanding emerged. They recognized that the surviving pieces of the original ecosystem mattered more than anyone had expected. Buried seeds, sheltered microorganisms, patches of intact soil, fallen wood, fungi, insects, and animals that endured below the surface all became known as biological legacies. These remnants supplied the living foundation from which recovery expanded. Recolonization from distant forests remained important, yet the strongest influence often came from life that had never truly disappeared. The eruption had also created an exceptional scientific design without anyone planning it. Disturbance varied from one location to another, forming a broad gradient across the mountain. Areas nearest the crater experienced nearly complete sterilization, while regions farther away retained increasing amounts of surviving biological material. Permanent study plots established during 1980 allowed scientists to compare each level of disturbance through the decades that followed. Because every plot was observed repeatedly using modern ecological methods, the resulting record became the longest continuous study of post-volcanic ecological succession ever assembled. The lessons extended far beyond one mountain. Forest managers, restoration ecologists, and conservation planners around the world began applying the concept of biological legacies after wildfires, hurricanes, volcanic eruptions, and commercial logging. Preserving surviving trees, soils, and living communities became recognized as a powerful way to encourage natural recovery. The decision to leave much of the blast zone untouched, despite early calls for widespread salvage logging and extensive replanting, eventually proved invaluable. The mountain demonstrated that allowing natural processes to continue could reveal ecological principles impossible to discover through intervention alone, reshaping the science of ecosystem recovery for generations that followed. Water remembers change in ways that stone cannot. After the eruption, Spirit Lake no longer matched the familiar outlines carried in maps, photographs, or memory. The debris avalanche poured into the basin with overwhelming force, filling large portions of the lake with shattered rock, broken forest, and volcanic sediment. Its surface rose by about 60 meters, which is about 197 feet, while its shoreline shifted into unfamiliar shapes. Depths changed, coves disappeared, and entirely new margins emerged where dry land had once stood. The lake beside which Harry Truman had spent 52 years no longer existed in its former form. Looking down from the air during the first days after the eruption revealed a scene unlike any ordinary mountain lake. The water was almost completely hidden beneath an immense floating blanket of timber. Millions of trees, stripped from surrounding slopes by the lateral blast and swept into the basin by the surging debris, gathered into a tangled mass that stretched across the surface. From above, Spirit Lake resembled a sprawling log storage yard instead of open water. The movement of waves had almost vanished beneath the weight of trunks pressed tightly together. Scientific surveys painted an equally startling picture beneath that floating cover. Hot volcanic debris had driven water temperatures close to boiling in some locations. Dissolved oxygen had nearly disappeared, leaving conditions unsuitable for fish and most other familiar aquatic life. Hydrogen sulfide accumulated as organic material decomposed, creating water hostile to complex organisms. Trout and salmon vanished, along with the thriving recreational landscape that had supported visitors for decades. Early observers regarded the lake as biologically finished, its ecological future reduced to uncertainty. Life, nevertheless, returned through forms almost invisible to the human eye. Within months, microorganisms adapted to heat and oxygen. Poor conditions established themselves throughout the water. Thermophilic bacteria flourished in warmer areas, while anaerobic species multiplied where oxygen remained scarce. They fed upon the enormous supply of organic material delivered by the eruption, including submerged logs, forest debris, and sediment washed from surrounding slopes. During this period, the lake functioned largely as a microbial ecosystem, with microscopic life-transforming material left behind by catastrophe into the foundation for future biological communities. As temperatures gradually declined and water chemistry stabilized through the passing years, increasingly complex organisms appeared. Phytoplankton multiplied where sunlight reached the water. Zooplankton followed, feeding upon those microscopic plants. Aquatic invertebrates established breeding populations, and amphibians eventually occupied sheltered shallows around the expanding shoreline. Fish were absent immediately after the eruption, and none have been deliberately reintroduced. The developing food web has continued assembling itself without the apex aquatic predators that once shaped the lake before 1980. The floating timber has remained one of the lake's defining features. More than 45 years after the eruption, the immense log mat still drifts across the surface, carried by changing winds and seasonal currents. Gradually, the wood softens, sinks, and becomes habitat for countless smaller organisms. Each passing year folds another portion into the recovering ecosystem below, while preserving a visible reminder of the eruption's opening moments. Spirit Lake today reflects both loss and renewal. Clearer water now surrounds sections of the drifting logs. Amphibians occupy its edges, birds search its shallows for food, and the crater of Mount Saint Helens rises beyond the surrounding forest. The lake is no longer the one Harry Truman cherished. It has become another landscape entirely, shaped by destruction, sustained by adaptation, and continuing to evolve with every passing season. The morning of the eruption eventually became more than a chapter in volcanic history. It grew into a turning point for the science itself. Never before had a major volcanic event been observed with such an extensive network of instruments, field teams, photographs, seismic records, gas measurements, and eyewitness accounts already in place before the explosion began. Every success and every mistake became part of a record that researchers around the world would examine for decades. The mountain had rewritten its own landscape, and in doing so, it also reshaped the methods used to understand dangerous volcanoes everywhere. Among the most significant lessons was the recognition that volcanoes do not always release their greatest force upward. Before 1980, hazard assessments concentrated on towering eruption columns, pyroclastic flows racing down valleys, and lahars following river channels. The collapse of Mount Saint Helens demonstrated that the side of a volcano could fail first, directing extraordinary energy outward across the landscape. From that point onward, evaluations of volcanic danger routinely included the possibility of lateral blasts. Whenever a restless volcano begins swelling or deforming today, one of the earliest questions considers whether part of its flank could collapse before the eruption fully develops. The response also transformed scientific institutions. In 1981, the David Johnston Cascades Volcano Observatory was established in Vancouver, Washington. Named in honor of the volcanologist who remained at his observation post until the final moments, the observatory became the principal center for monitoring volcanoes throughout the Cascade Range. Its responsibilities expanded over the following years, supporting research, hazard assessment, emergency planning, and public communication across much of the western United States. Knowledge gathered from Mount Saint Helens continued growing through the work carried forward within its laboratories and field programs. The influence soon reached far beyond North America. In 1986, the Volcano Disaster Assistance Program was created to send experienced scientists rapidly to volcanic emergencies across the world. Many of its earliest members had worked directly on the Mount St. Helens crisis, carrying practical lessons earned through experience instead of theory alone. Since then, the program has responded to more than 30 volcanic emergencies on several continents, helping governments interpret warning signs, improve monitoring, and organize evacuations before eruptions place communities in immediate danger. Those advances proved their value only a few years later. During the unrest at Mount Pinatubo in the Philippines in 1991, scientists with experience from Mount St. Helens joined an international monitoring effort. Hazard maps reflected lessons learned from the lateral blast, deformation studies, and changing volcanic gas emissions. Their recommendations persuaded Filipino and American authorities to evacuate tens of thousands of people before the volcano produced a volcanic explosivity index 6 eruption, larger than Mount St. Helens. The evacuation is widely regarded as one of the greatest successes in volcanic disaster preparedness, preventing a tragedy that otherwise could have claimed many thousands of lives. One legacy reached directly back to David Johnston's own research. His investigations into volcanic gas emissions sought reliable patterns linking changes in gas chemistry with approaching eruptions. The evidence available during his lifetime remained incomplete, yet the decades that followed confirmed the value of that work at volcanoes across the globe. Monitoring the composition and release of volcanic gases is now considered one of the essential tools for forecasting eruptive behavior. In that enduring practice, observations begun on one mountain continue guiding decisions wherever restless volcanoes rise above the horizon. The story did not conclude when the ash drifted away and the headlines began to fade. The landscape continued changing through days, months, and years, revealing that an eruption is often measured not only by its most violent morning, but also by the long conversation between magma, rock, water, and time that follows. Mount Saint Helens remained active after 1980, continuing to reshape itself, while scientists watched with a level of attention no volcano in the region had ever received before. During the remainder of 1980, the volcano produced 5 additional explosive eruptions. Each event was smaller than the catastrophe that transformed the mountain, yet each confirmed that molten rock still occupied the system below. Activity gradually shifted away from explosive destruction toward construction. Between 1980 and 1986, thick dacite lava rose into the crater and accumulated as a growing lava dome. Instead of racing across the landscape, this magma emerged with remarkable viscosity, piling upon itself in layers that slowly rebuilt part of what had been removed. The mountain was already beginning another chapter, adding new rock where so much had vanished. A different rhythm emerged in 2004. Small earthquakes increased beneath the crater, followed by bursts of steam that announced another period of unrest. Soon afterward, fresh dacite lava began rising again. This new dome expanded within the great horseshoe-shaped crater, growing at rates reaching several cubic meters each second. The process lacked the towering ash columns and sweeping devastation remembered from 1980, yet it carried enormous geological importance. Instruments recorded continuous change as molten rock steadily forced its way upward, demonstrating that the volcanic system remained alive beneath the surface. Over the following 4 years, continuing through 2008, the dome climbed more than 400 meters above the crater floor, which is about 1,312 feet. The enlargement could be measured precisely by monitoring equipment and, during clear weather, observed from Johnston Ridge. Visitors looking across the crater witnessed a mountain rebuilding itself, piece by piece. Growth unfolded at a pace suited to geology instead of human expectation, with every new layer recording pressure released from deep within the earth. One of the most remarkable changes involved something that seemed impossible after the heat of the eruption. Between the older lava dome and the newer one, a glacier gradually formed. Snow collected within the shelter of the crater walls, where sunlight reached the ground for shorter periods, and summer warmth failed to remove each winter's accumulation. Layer settled upon layer until flowing ice developed once again. The same crater that had erased glaciers within moments during 1980 became the birthplace of fresh ice only a few decades later, offering another reminder that destruction and renewal often occupy the same landscape. Today, the mountain is observed by one of the most comprehensive volcanic monitoring networks anywhere on Earth. Seismometers, global positioning system stations, gas sensors, tiltmeters, and satellite radar measurements capable of interferometric synthetic aperture analysis work together to detect movements far smaller than earlier generations could imagine. These instruments exist because of the lessons learned through loss and perseverance. The current assessment from the United States Geological Survey does not indicate that another eruption comparable to 1980 is imminent. Even so, Mount Saint Helens remains an active volcanic system. Magma still occupies the depths below, and the difference between not imminent and not possible remains as meaningful today as ever. Beyond the reshaped crater of Mount Saint Helens, the horizon continues in a procession of volcanic summits stretching across the Pacific Northwest. Each peak appears to stand alone, separated by forests, rivers, and valleys, yet all belong to a single geological system that has been operating for millions of years. Deep beneath the landscape, the Juan de Fuca Plate continues descending below the North American Plate. As that slab sinks into the mantle, water released from the descending rock lowers the melting point of the surrounding mantle, generating magma that slowly rises toward the surface. The process has not ended, nor does it show signs of slowing. Every volcano in the chain is another expression of that continuing movement within the earth. The Cascade Volcanic Arc includes Mount Baker, Glacier Peak, Mount Rainier, Mount Saint Helens, Mount Adams, Mount Hood, Mount Jefferson, the Three Sisters, Newberry Volcano, Crater Lake, Mount Shasta, Medicine Lake, and Lassen Peak. Each mountain has its own history, personality, and eruptive rhythm, yet all share the same deep origin. Some have remained peaceful throughout recorded history, while others have erupted within the past few centuries. Geological time measures their intervals differently than human memory, making centuries appear as little more than brief pauses between chapters. Among them, Crater Lake tells one of the most dramatic stories. Around 7,700 years ago, the volcano once known as Mount Mazama produced a volcanic explosivity index, 7 eruption, far larger than the eruption of Mount Saint Helens. The eruption emptied so much magma from beneath the summit that the mountain collapsed inward, leaving an immense caldera. Ash spread across much of the Pacific Northwest, and indigenous communities preserved memories of the catastrophe through oral traditions passed from one generation to the next. Rain and snowfall gradually filled the caldera over many centuries, creating one of the deepest lakes in North America, a landscape whose beauty began with extraordinary destruction. Volcanologists now regard Mount Rainier as presenting the greatest overall hazard within the Cascade chain. That assessment does not arise from an expectation of an imminent eruption. Instead, it reflects the enormous quantity of glacial ice covering the volcano. More ice rests upon Mount Rainier than on any other peak in the contiguous United States. If volcanic heat or structural collapse were to mobilize that frozen mass, lahars could race through river valleys toward heavily populated communities within only a few hours, carrying rock, ash, trees, and water across the lowlands. Those valleys contain neighborhoods, schools, hospitals, highways, and businesses serving tens of thousands of people. Automated lahar warning systems, equipped with sirens, have therefore been installed in several downstream communities. Depending on the size and speed of a lahar, evacuation time may range from 30 to 45 minutes. Within that brief interval, families, workers, teachers, emergency responders, and travelers would all need to reach higher ground before the flow arrived, making preparation as important as the warning itself. Running through every mountain in the Cascade chain is the same lesson revealed by Mount Saint Helens. Scientific evidence can identify danger, estimate probabilities, and improve warning systems, yet every recommendation eventually meets communities where people build homes, establish livelihoods, and form lasting attachments to the land. The balance between geological reality and human life remains an ongoing conversation, one that continues wherever these volcanoes rise above the forests, waiting through spans of time much longer than any single lifetime. The morning left another mark that could not be photographed. It spread through the atmosphere itself, shaping where people heard the eruption and where they heard nothing at all. Across the Pacific Northwest, sound followed pathways that seemed to ignore distance, creating one of the most unusual observations ever recorded during a volcanic disaster. Communities close to Mount Saint Helens expected an overwhelming roar. Many never received one. In Portland, Oregon, roughly 80 kilometers, which is about 50 miles south of the volcano, countless residents reported no tremendous explosion. The morning appeared ordinary until ash began drifting from a sky that had recently been clear. There had been no booming signal, no prolonged rumble crossing the horizon. For many households, the first indication that history had shifted arrived as fine gray particles settled onto streets, rooftops, and parked cars. A similar pattern appeared farther north. Seattle, located about 175 kilometers, which is about 109 miles from the volcano, also lay within the strange region where the eruption produced little or no audible warning for many listeners. People watched reports emerge, saw the changing sky, and learned of the catastrophe through observation and communication rather than through sound. One of the largest volcanic explosions ever documented in the United States unfolded without the dramatic noise many expected to accompany such an event. Far beyond this zone, the experience reversed. Across parts of British Columbia, residents described repeated booming noises that resembled distant artillery. In Montana and Idaho, people paused to search for an obvious source that never appeared. One woman living in a small Montana community contacted the local sheriff because she believed someone nearby was firing weapons. Northern California also received reports of distinct detonations carried across remarkable distances. The atmosphere had delivered the sound hundreds of miles from its source while withholding it from places much closer. The explanation rested high above the landscape. Sound waves do not always travel in straight lines through the air. Changes in temperature between atmospheric layers, combined with differences in wind speed and direction, bend those waves through a process known as acoustic refraction. Instead of remaining near the ground, much of the energy from the eruption curved upward into the atmosphere. Farther away, those refracted waves gradually bent downward again, returning to the surface in a broad ring surrounding the volcano. The atmosphere behaved like a giant lens, redirecting sound into unexpected places while leaving a broad acoustic shadow close to the mountain. That discovery carried practical importance, extending beyond this single eruption. Human hearing cannot always serve as a dependable warning during major natural events. People in Portland received no audible indication that an enormous eruption had occurred only 80 kilometers, which is about 50 miles away. Their first evidence came from ash, already arriving overhead. Under different circumstances involving a faster moving hazard, waiting for sound could have wasted precious time. The pattern remains one of the eruption's most remarkable legacies. An explosion releasing energy equivalent to about 26 megatons of trinitrotoluene passed unheard by many living within an hour's drive of Mount Saint Helens, while voices across Canada described unmistakable thunder from beyond the horizon. The geography of sound followed rules written in the atmosphere, and those rules traced a map entirely different from the geography of danger. History often remembers Harry Truman as a symbol before it remembers him as a person. During the weeks before the eruption, newspapers and television broadcasts found in him a character audiences immediately understood. He was portrayed as the stubborn mountain caretaker who refused to let government officials or scientists tell him where he could live. The image fit comfortably within a familiar American story, one built around independence, determination, and affection for a rugged landscape. That portrait contained genuine pieces of his personality, although it left much of his life outside the frame. Harry Truman was outspoken, humorous, and openly dismissive of repeated evacuation requests. Reporters returned because he offered memorable conversations and colorful remarks at a moment when uncertainty surrounded Mount Saint Helens. Viewers saw a man who appeared entirely confident in his decision to remain beside Spirit Lake. Confidence, however, was only one part of the life he had built there, and understanding the rest changes the meaning of the choice he ultimately made. 5 years before the eruption, his wife, Edna, had died. Together, they had spent 37 years building and operating Spirit Lake Lodge. They welcomed visitors through changing seasons, repaired buildings, worked long days, celebrated holidays, and shaped nearly every corner of the property together. The lodge held more than furniture and guest rooms. It preserved routines repeated across decades, photographs gathered through a shared life, familiar paths leading to the dock, and countless ordinary memories that accumulated year after year. After Edna's death, friends noticed changes. Harry devoted less attention to maintaining the property, accepted fewer guests, and drank more often. Even so, leaving the lodge meant leaving the place where almost every memory of their marriage remained present. His own words reveal that attachment more clearly than any headline. During interviews, he explained that he and Edna had spent 37 years loving, working, arguing, laughing, dancing, and truly living beside their mountain and lake. On another occasion, he said that if he abandoned his home, he would die within a week because he could not bear life anywhere else. Those statements sound less like a performance created for television cameras and more like the reflections of someone whose identity had become inseparable from a particular place. The public image carried consequences extending beyond one individual. Harry Truman gradually became an emblem of resistance. Other residents inside the exclusion zone watched those interviews, read those newspaper stories, and absorbed the message that remaining behind represented strength while evacuation suggested surrender. Scientists were attempting to communicate uncertain but growing danger, yet popular storytelling often celebrated refusal with greater enthusiasm than caution. That cultural current complicated an already difficult effort to persuade people that temporary departure could preserve lives without diminishing personal dignity. On the evening before the eruption, Harry spoke with a neighbor and remarked that the mountain seemed to be calming. There is little reason to believe he expected the following morning to unfold differently from many others. Dawn arrived, routines continued, and the lodge overlooked the same lake that had shaped his adult life. He did not meet the eruption while attempting to prove fearlessness. He remained because the landscape had become the final home of the life he and Edna had created together, and he believed that home would still be there when another ordinary day began. By the time Robert Landsburg recognized what was racing toward him, there was no practical path to escape. The collapsing flank of Mount Saint Helens had unleashed a laterally directed blast, moving across the landscape at extraordinary speed. He stood less than 6 kilometers, which is about 3.7 miles, from the crater, close enough that the advancing cloud was transforming the entire horizon. In those remaining moments, his attention shifted away from survival and toward the photographs already exposed inside his camera. The sequence he carried out has been reconstructed from the condition in which rescuers later found him. He rewound the exposed film into its protective canister. He removed that canister from the camera and placed it inside his backpack. He arranged the pack beneath his body before lying across it, using his own weight as a shield. Every action depended on the one before it. The canister offered protection from ash and debris. The backpack added another insulating layer. His body became the final barrier between the film and the searing material that would soon sweep across the ground. Those choices reflected careful reasoning completed within seconds, while a wall of superheated gas, ash, and rock fragments approached at tremendous speed. Even those precautions could not keep the eruption from leaving its signature on the images themselves. After recovery, technicians developed the film and discovered marks created by the violence it had endured. Heat had warped portions of the material. Fine scratches crossed several frames. Tiny bubbles and light leaks appeared where intense temperatures had begun to affect the emulsion despite the layers protecting it. The photographs became more than visual records of the eruption. The eruption had physically written part of its own history onto the medium that preserved it. The pictures revealed details unavailable from instruments alone. They showed the appearance of the expanding blast cloud from ground level at extraordinary proximity. Frame by frame, the advancing front occupied more of the landscape, reducing familiar features until nearly everything disappeared behind ash and turbulent gases. Variations in brightness, texture, and color offered additional clues about the density of the cloud and the changing conditions within it. Combined with measurements from seismometers and other monitoring equipment, those photographs helped volcanologists reconstruct the earliest stages of the lateral blast with greater confidence than would otherwise have been possible. For Landsburg, publication represented a lifelong professional ambition. He had hoped that one day his work would appear in National Geographic. That goal was fulfilled after his death. His photographs were published in the magazine's January 1981 issue, accompanied by an explanation of how they had survived because of his final decisions. Readers around the world encountered images that existed only because their photographer had chosen to preserve them instead of attempting one last, impossible escape. Many decades later, renewed interest in Landsberg's life inspired filmmakers to look beyond the famous photographs. Researchers discovered that his family had rarely spoken publicly about him. His original camera remained in family possession, and his journals still offered an intimate record of the person behind the lens. The photographs had always been celebrated, yet the patient observer who created them remained largely unknown. As that story gradually emerged, his final act came to represent more than professional dedication. It became the lasting expression of a man who believed that knowledge was worth protecting, even when time itself had almost disappeared. A walk across the northern side of Mount Saint Helens in the present day unfolds like turning the pages of several centuries at once. Every step crosses a different chapter of recovery. One hillside still carries the color of fresh volcanic deposits, while another supports growing forests that sway with birdsong and passing mammals. The transition is gradual enough to read with the eye, each change reflecting how much heat reached the ground and how much life endured beneath the surface. Few places on Earth display ecological time so openly across a single landscape. Closest to the crater, the pumice plains remain broad, pale, and open. Wind still shifts loose volcanic fragments across the ground, while scattered islands of vegetation continue their patient expansion. Lupine flowers brighten patches of ash, adding nitrogen to soil that once held almost none. Young conifers rise from cracks where moisture lingers a little longer after winter snow has disappeared. Many of these seedlings grow from mounds lifted by burrowing pocket gophers, whose tunnels carried buried soil upward decades earlier. Their work created small pockets where roots could gain a foothold. The trees remain modest in height, often reaching only a person's knees, where Douglas firs once stood nearly 60 meters tall, which is about 197 feet. Farther from the crater, the forest tells another part of the story. Thousands of fallen trunks still lie in remarkably orderly rows, all pointing away from the mountain, preserving the direction taken by the lateral blast. Time has softened their appearance. Moss is spread across bark that once seemed lifeless. Lichens trace pale patterns over weathered wood. Fungi work steadily through the timber, while insects carve tunnels that shelter countless smaller creatures. Seedlings frequently emerge from the length of these decaying logs, drawing moisture and nutrients from wood that has gradually become fertile ground. Material once described as debris now serves as the foundation for another generation of forest. Wildlife has woven itself back into these valleys with similar patience. Roosevelt elk travel through meadows that were stripped nearly bare during the eruption. Black bears search for berries along recovering slopes. Coyotes follow game trails between young stands of trees. Mountain goats navigate rocky ridges, while deer browse fresh vegetation across open clearings. Birds nest in shrubs, forage among standing snags, and circle above streams where aquatic insects have returned. The community remains younger and less diverse than the ecosystem that existed before 1980. Yet, each season adds another layer of complexity as relationships among plants, animals, fungi, and microorganisms continue to develop. One of the most revealing views appears where the protected National Volcanic Monument meets neighboring commercial forest land. On one side stand orderly plantations of Douglas fir, planted after the eruption and managed for timber production. Their uniform spacing and even canopy create an immediate impression of efficiency. Across the boundary, natural recovery unfolds without straight lines or predictable spacing. Open meadows blend into clusters of shrubs, scattered conifers, wetlands, fallen logs, and surviving remnants from before the eruption. The managed forest appears fuller, yet the naturally recovering landscape holds a richer mosaic of habitats that continues to teach ecologists how resilient living systems can be. Seen together, these places form a living record rather than a finished destination. The pumice plains preserve the memory of overwhelming heat. Recovering forests reveal where surviving roots, seeds, and soil communities found opportunities to begin again. Fallen timber marks the tremendous force that crossed the land while also nurturing new growth. The blast zone remains suspended between destruction and renewal, carrying both histories at once, with every passing season adding another line to a story that continues to unfold. The path to Johnston Ridge ends at a place where observation and remembrance share the same ground. Perched at an elevation of 1,314 meters, which is about 4,311 feet, the observatory stands on the ridge where David Johnston lost his life during the eruption. About 8 kilometers from the crater rim, which is about 5 miles, it remains the closest permanent public facility overlooking the volcano. Operated by the United States Forest Service, it welcomes visitors seeking to understand the mountain while continuing to serve as part of the scientific effort that watches over its activity every day. From the broad viewing windows, the crater opens across the landscape in almost the same direction Johnston watched on that Sunday morning. The distance has changed little. The angle remains strikingly familiar. Only the mountain itself has transformed. The graceful summit that filled his notebook sketches vanished within moments, leaving the horseshoe-shaped crater visible today. Calculations based on the eruption indicate that the lateral blast covered the distance to his observation post in roughly 30 seconds. Modern visitors stand where he once stood with the benefit of decades of knowledge, yet the view still carries the immediacy of those final observations. Science also returned to this ridge. Instruments linked to the monitoring network now record the smallest changes in the volcano, measuring earthquakes, ground movement, volcanic gases, and countless subtle signals that reveal conditions deep below the surface. The location was chosen with purpose. Cold water, too, demonstrated that meaningful observations could be gathered from this distance while maintaining a practical position for continuous study. The ridge that marked the end of Johnston's work became the foundation for the observatory that extended it. Every measurement collected here reflects lessons earned through experience that reshaped volcanic monitoring across the world. Another thread in this story belongs to Harry Glicken. As a graduate student, he had originally been scheduled to occupy the Coldwater Observation Post before another professional commitment altered those plans, and Johnston took the assignment instead. Glicken continued his career with extraordinary dedication, studying volcanic hazards with the same careful attention that had drawn him to Mount Saint Helens. 11 years later, during the eruption of Mount Unzen in Japan, he was caught by a pyroclastic flow while conducting field research. He became the second American volcanologist to lose his life during an active volcanic eruption, following the colleague whose place he had once been expected to occupy. The connection between Johnston and Glicken carries no need for embellishment. A mentor accepted an assignment that otherwise might have belonged to his student. Years later, the student met the same kind of force while pursuing the same calling on another continent, nearly 8,000 kilometers away. That is nearly 4,971 miles. Their lives formed separate chapters, joined by a shared commitment to understanding volcanoes, from close enough to gather knowledge that distant observation could never provide. Visitors eventually leave Johnston Ridge carrying photographs, memories, and a wider understanding of the mountain before them. The instruments remain, recording each tremor and every gradual change. The ridge itself continues to overlook the crater, linking present observation with a morning that transformed both volcanology and the landscape below. In that enduring view, discovery and remembrance occupy the same horizon, each giving lasting meaning to the other. Some scientific questions outlive the people who first ask them. David Johnston left behind one of those questions, carefully framed, measurable, and grounded in observations gathered on the slopes of Mount Saint Helens. His work centered on volcanic gases escaping from the mountain long before the eruption. He wanted to know whether those invisible emissions could reveal that magma was rising while the volcano still appeared comparatively calm. The idea reached beyond curiosity. If the gases changed first, they might provide an earlier warning than any method then available. The reasoning followed the behavior of magma itself. Deep below the surface, molten rock contains gases held in solution by immense pressure. As magma climbs toward shallower depths, that pressure steadily decreases. The dissolved gases separate from the molten material and begin moving upward through cracks and porous rock before the magma reaches levels where earthquakes become frequent or the ground begins to swell noticeably. Johnston believed these changing emissions formed an earlier chapter in the eruption process. If scientists learned to recognize those signals, they could gain valuable time before more familiar warning signs appeared. When Johnston arrived at Mount Saint Helens during the spring of 1980, only 2 scientists within the United States Geological Survey specialized in volcanic gas monitoring. He was one of them. His days often involved collecting samples from fumaroles, measuring the chemistry of escaping gases, and comparing each result with earlier observations. Every sample added another point to a growing record that he hoped would reveal consistent relationships between changing gas composition and volcanic behavior. The work demanded patience because meaningful patterns emerge through repeated measurements gathered over many weeks or months. His death interrupted that record before enough observations had accumulated to reach a firm conclusion. The notebooks, samples, and laboratory analyses remained, yet the central question continued without its principal investigator. Researchers who followed expanded the work at Mount Saint Helens, while similar studies began at volcanoes across many regions of the world. Instruments became more sensitive. Airborne measurements joined ground-based surveys. Satellites eventually contributed additional perspectives, allowing scientists to compare gas emissions with seismic activity, ground deformation, and thermal changes recorded during countless volcanic episodes. The evidence assembled over subsequent decades consistently pointed toward the conclusion Johnston had anticipated. Variations in volcanic gas composition frequently appear before earthquakes and surface deformation become unmistakable. One relationship proved especially valuable. Shifts in the balance between sulfur dioxide and carbon dioxide often accompany magma rising toward the surface, offering an important indication that conditions inside a volcano are changing. Modern observatories now include gas monitoring as a standard component of volcanic surveillance, placing Johnston's original research question at the center of everyday hazard assessment instead of its margins. There is a quiet symmetry in the outcome. Johnston devoted his final months to determining whether volcanic gases could reveal that an eruption was approaching. The answer eventually became yes. That conclusion arrived through decades of work by many scientists, supported in part by the measurements he gathered before the eruption claimed his life. His investigation reached beyond the span of his own career, continuing through the observations of others until the mountain, and many mountains after it, finally completed the answer he had begun to uncover. Few volcanic landscapes exist in isolation from the communities around them. Every active volcano becomes part of an ongoing conversation between geology, science, government, economics, and daily life. The negotiations that surrounded Mount Saint Helens during the spring of 1980 were not an unusual chapter in volcanic history. They reflected a pattern repeated across continents whenever people choose to live beside mountains that may remain inactive for generations before changing within hours. The same balance can be found around Mount Vesuvius in southern Italy. More than 3 million people live across the Naples metropolitan region, while the officially designated highest hazard area includes roughly 700,000 residents spread across 18 municipalities. Emergency plans describe how an evacuation would unfold before a major eruption, yet no evacuation of that scale has ever been carried out under real conditions. Scientists evaluate changing volcanic signals, while public officials must weigh schools, businesses, transportation, hospitals, and homes against an event that may arrive decades from now or remain absent throughout an entire lifetime. A similar challenge continues at Campi Flegrei, another volcanic system near Naples. Since 2005, the ground has risen by more than 148 centimeters, which is about 4 feet 10 inches. Swarms of earthquakes have accompanied that uplift, including the strongest event of the current period of unrest during June 2025. Authorities have maintained a yellow alert since 2012, recognizing measurable volcanic activity without concluding that an eruption is imminent. Every episode that settles without an eruption creates another layer of public familiarity, making future warnings more difficult because repeated alerts naturally reshape expectations. Across the Pacific Northwest, Mount Rainier presents a different expression of the same dilemma. Thick glaciers mantle its upper slopes, and valleys extending from the volcano contain neighborhoods, schools, highways, and essential infrastructure. Many communities occupy deposits left by earlier lahars, reminders that destructive volcanic mudflows have traveled these paths before. Automated warning systems monitor the volcano and can provide approximately 30 to 45 minutes of notice if a large lahar begins moving downstream. That brief interval reflects years of scientific planning, yet it also illustrates how little time remains once the hazard has already begun. In every one of these places, scientists continue making arguments that resemble those voiced around Mount Saint Helens before its eruption. Hazard maps are revised as knowledge improves. Monitoring networks become more sophisticated. Recommendations often favor wider safety margins because volcanic systems rarely conform to convenient boundaries. Alongside those assessments stand governments, businesses, landowners, and residents who must consider livelihoods, property, and communities shaped over generations. Neither side speaks from indifference. They are responding to different responsibilities while confronting uncertainty that cannot be removed completely. Mount Saint Helens left behind more than a transformed landscape. It demonstrated that exclusion zones, even when imperfect, save lives by keeping people away from the greatest danger. It also revealed that the distance between scientific recommendations and politically achievable decisions can become the place where consequences gather most heavily. That lesson continues wherever active volcanoes rise above populated horizons, inviting each generation to weigh evidence, patience, and preparedness against forces that follow neither calendars nor human preference. Standing within the blast zone today offers an unusual sense of perspective. A single landscape carries two clocks at once, each moving at its own pace. One belongs to human memory, measured in the roughly 46 years that have passed since the eruption of 1980. The other belongs to the mountain itself, measured across hundreds of thousands of years of repeated construction, collapse, and renewal. Both histories occupy the same ground, yet they unfold at profoundly different speeds, revealing that the meaning of change depends entirely upon the span of time through which it is observed. From the scale of a human lifetime, 46 years represents meaningful change. Children who watched ash drift across the sky have become grandparents. Students who first entered the blast zone carrying notebooks eventually returned as professors leading new generations of researchers. Entire scientific careers have unfolded while documenting the return of plants, insects, mammals, fungi, and forests. Visitors who first encountered broad gray plains now walk among expanding stands of young trees. The transformation has occurred within living memory, allowing people to witness ecological recovery that is usually far too gradual to observe directly. What once appeared almost lifeless has become an outdoor record of resilience, shaped day after day by ordinary seasons instead of dramatic moments. The mountain keeps a different calendar. Mount Saint Helens has experienced repeated eruptive periods for approximately 275,000 years, interrupted by intervals of relative calm that sometimes lasted centuries. The crater created during the 1980 eruption appears permanent when viewed across a human lifetime, yet geology treats it as another temporary feature. Lava domes have already begun filling part of the opening, and future eruptions may continue building new rock until another summit cone gradually rises. Even that future peak will not remain unchanged forever. Every volcanic mountain carries the record of earlier landscapes buried beneath newer ones, each generation of rock preserving traces of events that later eruptions partially erase before adding another layer to the story. The forest that covered these slopes before 1980 also belonged to this repeating cycle. Towering Douglas fir trees seemed timeless to those who lived among them, although they had taken root in soils produced by eruptions that occurred long before written history reached this region. Layer upon layer of volcanic ash weathered into fertile ground, supporting forests that supplied fallen logs, rich organic matter, and habitat for countless species. The eruption removed much of that forest, yet the same volcanic material that caused such sweeping destruction continues nourishing the next generation of plants spreading across the landscape. Seedlings now draw nutrients from deposits left by the very event that cleared the previous woodland, continuing a cycle repeated many times across the volcano's history. Viewed across geological time, creation and destruction become parts of the same continuous process. Fresh lava fractures beneath changing weather. Volcanic ash gradually breaks into mineral particles that enrich the soil. Mosses arrive, followed by flowering plants, shrubs, and trees. Animal communities expand as food and shelter increase. The mountain reshapes the conditions that allow life to return, and life gradually reshapes the volcanic deposits left behind. Neither process remains fixed, because each continually influences the other across spans far longer than a human lifetime can fully witness. Perhaps that is the deepest lesson preserved within the blast zone. Human lives naturally measure change in decades, while volcanoes measure it across intervals almost beyond imagination. Mountains, forests, lakes, and river valleys appear enduring because they outlast generations, yet each remains part of an unfolding landscape that never truly settles. What appears to be catastrophe within one lifetime becomes another chapter in a story that has continued for hundreds of thousands of years, carrying the same mountain through one transformation after another, without haste and without conclusion. Every landscape tells the story of the forces that shaped it, although those stories often unfold across spans far longer than any human life can witness. The valleys, forests, rivers, and mountains of the Pacific Northwest appear settled and enduring, yet each owes its existence to countless volcanic events spread across millions of years. The eruption of May 18th, 1980, was one chapter in that continuing history, dramatic within human memory, yet entirely consistent with the geological processes that created the region itself. The Cascade Range exists because the Juan de Fuca Plate continues descending beneath the North American Plate along the Pacific Northwest coast. As that oceanic crust sinks into the mantle, portions of it release water that encourages surrounding rock to melt. Magma rises through the crust, gradually building volcanoes over repeated eruptive cycles. Those volcanoes supply ash, lava, and fragmented rock that become part of the surrounding landscape. Rivers occupy valleys, shaped partly by erosion and partly by volcanic deposits left behind by lahars and earlier eruptions. Fertile lowlands, forested slopes, and rugged mountain peaks all reflect this long partnership between fire, water, and time. The eruption of 1980 added approximately 1 cubic kilometer, that is nearly 0.24 cubic miles, of fresh volcanic material to the landscape surrounding Mount Saint Helens. At first, much of that deposit appeared barren, composed of ash, pumice, and shattered rock. Weather gradually began breaking those materials into finer particles. Rain, freezing winters, plant roots, fungi, and microorganisms slowly transformed the fresh deposits into developing soil. The lupine that spread across the pumice plains helped accelerate that change by adding nitrogen to the ground through its partnership with bacteria living within its roots. Each growing season has continued preparing the surface for shrubs, conifers, and the richer forest communities that will follow across the coming centuries. Elsewhere in the Cascade Range, another volcano demonstrates the same pattern across a longer interval. Crater Lake occupies the collapsed summit of the former Mount Mazama, following a massive eruption approximately 7,700 years ago. That eruption emptied much of the magma chamber beneath the volcano, allowing the summit to collapse into a broad caldera. Rain and snowmelt gradually filled the basin, creating one of the deepest lakes in North America and one of the most striking landscapes in the United States. Visitors now encounter clear blue water where an eruption once transformed the mountain, illustrating how geological change can eventually become the setting for remarkable beauty. The old growth Douglas fir forest that covered the slopes around Mount Saint Helens before 1980 had grown from soils enriched by eruptions that occurred centuries and millennia earlier. Those towering trees existed because previous volcanic activity had supplied minerals that weathered into productive ground. The forest that will one day replace the one lost during the blast is beginning from the ash deposited on May 18th, 1980. The same volcanic material that buried the landscape is becoming the foundation for another generation of forests, continuing a cycle repeated throughout the history of the Cascade Range. The lives lost during the eruption became part of that same landscape whose beauty had drawn people to its valleys, lakes, and forests. Their story cannot be separated from the geology that raised the mountain itself. The forces that transformed the land also created the fertile soils, towering forests, and remarkable scenery that surrounded it. Across geological time, destruction and renewal remain inseparable companions, each preparing the ground for what follows. Night settles across the slopes of Mount St. Helens as it has on countless evenings before, while instruments remain awake in every season. Seismometers anchored in bedrock continue recording tiny fractures, shifting fluids, and faint vibrations moving through the volcano. Most of these signals are too small for people to notice without specialized equipment, yet together they form the ongoing conversation of a volcanic system that has not reached a permanent ending. The eruptive episode that transformed the mountain in 1980 continued in a different form during the dome-building eruptions that resumed in 2004, reminding scientists that volcanic landscapes evolve through intervals measured in decades as well as centuries. The Great Horseshoe-shaped crater remains carved into the northern face of the mountain. It stretches for about 3 kilometers, which is about 2 miles, across, still revealing the force that reshaped the summit. On clear days, it can be seen from Johnston Ridge and from distant viewpoints across the surrounding region. Within its walls, the lava dome continues cooling, while glaciers press slowly against hardened volcanic rock. Steam still rises from fumaroles, carrying heat from deep underground into the open air. The crater has changed since 1980, yet its defining form endures, preserving the visible record of an eruption whose effects continue unfolding. Across the pumice plains, another kind of record grows. Young conifers stand where open ash once dominated the landscape. Lupine continues enriching the ground, preparing it for future forests. Roosevelt elk travel through valleys that gradually regained grasses and shrubs. Birds nest among weathered trunks left by the lateral blast, while insects, fungi, and burrowing mammals reshape the surface a little more each year. The place carries sounds that did not exist during the months immediately following the eruption when fresh deposits supported very little life. Recovery has never followed a straight path, yet every season adds another layer to the living landscape. The scientific question that guided David Johnston's research has found a meaningful answer. Careful monitoring has demonstrated that changes in volcanic gases, especially the changing relationship between sulfur dioxide and carbon dioxide, often appear before other warning signals become unmistakable. That discovery transformed volcano monitoring around the world, although each improvement introduced another responsibility. Instruments must detect those changes with greater precision, scientists must interpret the evidence accurately, and public officials must decide when uncertain information has become strong enough to justify action. Every advance in knowledge carries another decision waiting beyond it. The memorial at Johnston Ridge honors the 57 people who lost their lives during the eruption, including David Johnston, Harry Truman, Robert Landsburg, and many others whose stories unfolded along different paths that morning. Their names remain connected through a single event that forever changed the science of volcanic hazards. Monitoring networks covering Mount Saint Helens today exist because researchers sought to understand every lesson the eruption revealed, including those learned through profound loss. The mountain continues shaping itself without haste. The dome changes, glaciers move, forests spread, rivers carry volcanic sediment, and fresh soil develops from ash deposited decades ago. The Cascade Range itself owes its existence to the same geological forces that remain active beneath Mount St. Helens today. Every night, the instruments continue gathering their measurements, preserving another page in a record that has not reached its final chapter. The mountain continues its work, and those listening continue theirs.